This lecture is about solution to some selected problems of Chapter 10 on the topic of columns. I have already uploaded a lecture on columns which consists of theories related to columns. We have already discussed two theories, one for centric loading, which is Euler Formula, and then another is for eccentric loading, which is Secant formula. So now I want to solve some numerical problems, some selected problems from the exercise, because there are so many problems I cannot upload solution to all of them, but I have chosen some of them for your reference and I hope this will help you. So moving forward, the first problem which I have selected for the students is problem number 1017 from the exercise, chapter number 10, problem number 17. The statement of the problem is a column of 22 feet effective length. So already LE, effective length, is given. We do not need to know either both ends of the column are pinned or fixed, or one end is pinned, other is fixed. We do not need to know the boundary conditions. The effective length is directly given. It is made by welding two 9 into 0.5 inch plates. There are two plates at the ends. Here is one plate, here is another plate. The plate has length of 9 inches and width equal to 0.5 inch each of these plates. Okay, it is welded to W8 cross 35 inch beam. In between these two plates we have a W beam, W8 35. Determine the allowable centric load if a factor of safety of 2.3 is required. So factor of safety is given. We have to find allowable centric load. It is centric load, so we need to use Euler formula. P allowable is required. E is given. E is 29 into 10 power 6 psi. Okay. Now, if the effective length is given, we do not need to find LE over R because LE is already given. Now, the beam has a tendency to either deflect, rotate around y-axis or rotate around x-axis. In both the case, LE is same. So boundary conditions in xz plane and yz plane are same. Length is in z-axis, which is not visible in this expression, in this figure. Actually, this beam is like here is a W beam. Sorry, this column is like is a W section, and then there are two plates welded to this W section, and then there is a length of the beam in the third dimension, which is not shown in the figure. So this beam is like this. We have been given the cross section. Okay, so we need to find moment of inertia I around x-axis and around y-axis. This is over y-axis, this is x-axis, and length is z-axis. The column can buckle in either xz plane or yz plane. So in whichever plane I is minimum, the column will buckle in that direction. So we have to find Ix and Iy. Whichever is minimum, we have to use the same I and we have to solve the problem. Okay, we already know using Euler formula, P critical is pi square E I divided by LE square. Pi is a constant, E is given, LE is given. we have to find Ix and Iy. Whichever is minimum, we will use that one. Column will buckle in the minimum I direction. Once we find P critical, we can find P allowable from P critical. It is P critical divided by factor of safety. Okay, so we only need I minimum. For I minimum, we have to find Ix and Iy. Among them, whichever is minimum, that will be our I minimum. So let us start it. As it is W835 beam, so we can find Ix and Iy from the appendix tables, and then we can find I for the end plates, this plate and this plate manually. So let us move. Okay, one more thing. Since on the x-axis the plates lie, the centroid of the plates lie on the x-axis, so D is 0 for the plates around x-axis, and then if we want to find I around y-axis, I for the W section can be found from the table, but we need D for plate, which is equal to half of the height of the I section, the width of the I section plus half of the plate width. So let us move and solve this problem. Okay, as we move to the tables from the book for W835 beam, Appendix C, W shapes, W835, it is in inches, so W835 is here, it's W835. Okay, here is x-axis, here is y-axis. We can see the x and y are similar to that given in our problem. We can see the x is perpendicular to the web of the I section, W section, and y is along the web. It is similar to that given in the appendix. X is perpendicular to the web and y is along the web. So Ixx for W35 is 127, Iyy is 42.6 inch power 4. Similarly, we also need this width of the flanges to find D for the column for the plates. So width for the flange for each flange is 8.02 inches. Okay, so let us move and so okay, we also need area of the column, AD square. We will need AD square. So area of the cross section. So area of the cross section for plate, we will need that. Okay, it is enough. Let us move. Ix was 127 inch power 4 from the table. Iy was 42.6 inch power 4, and width of the flange BF was 8.08 inch. Okay, this is for I section. For W835 section, similarly for the plates, area of each plate is 9 into 0.5 square inch, so it is 4.5 square inch. Okay, I for each plate, let me draw it here again for your understanding. W section, and here is a plate, here is another plate, this is x-axis, this is y-axis. Okay, so this is D for the plate. D will be half of BF, this is BF, half of BF plus half of the thickness of the plate, which is 0.5 by 2. Okay, so this thickness is 0.5 and the height is 9. So around x-axis, Ix for the plate is simply 1/12 into 0.5 into 9 cube, which becomes 30.375 inch power 4. Iy will be 1/12 into 9 into 0.5 cube. Since around when we are finding I around y-axis, the centroid of the total cross section and centroid of the plates do not match. That is why we have an offset distance d. So we have to add here AD square. A is area, which has been found here for area of the plate, 4.5. D is this value, half of BF, half of 8.02 plus half of the plate thickness, half of 0.5. So Iy of the plate becomes 81.758 inch power 4. So we have found Ix and Iy for the W section. Similarly, Ix and Iy for the plate. So we can find total Ix and total Iy. Total Ix will be sum of the Ix for W section and the plate. So 127 plus 30.375. Total moment of inertia. So total Ix is, sorry, there are two plates. So we have to multiply the plate I with 2. 2 times I for the plate around x-axis. So total I around x-axis is 187.75 inch power 4. Similarly, I around y-axis is Iy for the W section plus 2 times Iy for the plates. So Iy for the W section is 42.6 plus 2 times Iy for the plates, 81.758. So this becomes 206.116 inch power 4. Among these two values of moment of inertia, Ix is minimum. 187.75 is lesser than 206.116. So Ix is I minimum actually. It means the column will rotate or buckle around x-axis because I is minimum around x-axis. So we will use Ix in our further calculations. P critical is equal to pi square E I minimum divided by LE square. All other values are given. E is given, LE is given, pi is known, I minimum is now calculated. So by putting all the values, I is 29 into 10 power 6 psi. This is already in inches. LE was given as 22 feet. So 22 into 12 inches. So we can find P critical as 771 kilopounds. But we were asked to find P allowable. So P allowable is equal to P critical divided by factor of safety. Factor of safety is given, which is 2.3. So P allowable is equal to 335 kilopounds. This was required. So what we have done is, as LE was given, which was 22 feet, and LE is same around both X and Y given in the problem. So we need to find I minimum. The column will buckle around an axis around which moment of inertia will be minimum. So we have found both of the moment of inertia Ix and Iy for the W section and for the plates, and we have added them. There are two plates, so I for plate is multiplied with 2. The one with the minimum value is Ix. We have chosen it. We have calculated P critical, and then P allowable is equal to P critical divided by 2 divided by factor of safety 2.3. So P allowable is calculated. Let us move towards our next problem. The next problem which I have selected is problem 10.21. Interestingly, you can see that the column given in this problem, in this figure, is horizontal. So it is a proof that columns can be horizontal. The difference between a column and beam, which we have discussed in the theoretical part, was that columns are under normal load while beams are under transverse loads, bending moment. So here is a column which is horizontal and it is under axial load, so that is why we are calling it column, despite that it is horizontal. So there is no such definition that column will always be vertical. Columns can be horizontal, but the load will be axial in a column. In beam, a beam can be vertical or horizontal, but the load will be transverse. There will be bending moment in the beam. Okay. The statement of the problem is, the uniform brass bar AB has a rectangular cross section and it is supported by pins and brackets as shown. NA and NB are pinned to brackets, and what we are asked here is, each end of the bar can rotate freely about horizontal axis through the pin, but rotation about vertical axis is prevented. If we see this pin, it can rotate around horizontal axis, but rotation around vertical axis is stopped by these brackets. So it means this column has pin-ended connections around horizontal axis, but it is fixed around vertical axis. So we have two possible rotation directions, around vertical axis or around horizontal axis. So if we consider rotation around horizontal axis, the pin in the column is pin-ended at both ends. If we consider rotation around vertical axis, the column is fixed at both the ends. Okay, so it means for horizontal axis, around horizontal axis, LE is equal to L, because both ends are pinned, and around vertical axis both ends are fixed, so LE is equal to 0.5 L. We have already studied this in the theory. You can see when both ends are pinned, LE is equal to L. When both ends are fixed, LE is equal to half of L. So we will use LE is equal to L for rotation around horizontal axis, and LE equal to half of L for rotation around vertical axis. Okay, what is asked? In part A, determine the ratio B over D for which the factor of safety is same about horizontal and vertical axis. We have to find B over D. B and D are dimensions of the column, thickness and depth. When factor of safety is same about horizontal and vertical axis. For part A, if factor of safety about horizontal and about vertical axis are same, since applied P is same around both axes, so it means if factor of safety is same, it means P critical is same about horizontal and about vertical axis. So we will use this expression in part A. We will find expression for P critical around horizontal and around the vertical axis, and then we will equate them. In part B, we need to determine the factor of safety. In part B, we can use any of them, either horizontal or vertical, because both are same. Numerical values are given, so we will find factor of safety. Okay, so let us move to the solution. Previous one was problem number 1017. Now we are solving problem number 1021. Okay. P critical around horizontal axis is pi square EI over LE square. Around horizontal axis, LE is equal to L because both ends are pinned. We have already discussed it. I around horizontal axis is equal to, let us see here, this is horizontal axis, and if the beam rotates around horizontal axis, so the depth is D. So we have to take cube of D. So I is equal to B D cube divided by 12. So P critical around horizontal axis becomes pi square E B D cube divided by 12L square. Similarly, P critical vertical is equal to pi square EI over LE square. So around vertical axis, LE is equal to half of L, as we have discussed. Around vertical axis, both the ends are fixed. Similarly, I will be dB cube. In this case, B is depth, so dB cube divided by 12. By putting all the values, it becomes pi square E dB cube divided by 3L. Okay, so as in the problem, it is given that factor of safety is same around both the axes. So we can use, for part A, we can use P critical around vertical axis is equal to P critical around horizontal axis, since it has the factor of safety is same around both the axes. So by putting the above expressions, pi square E dB cube divided by 3L is equal to pi square E b d cube divided by 12, sorry, this is L square. So b over d becomes 1 over 2. This was required in part A of the problem to determine the ratio of p over d. In part B, in part A, b over d was required. In part B, d is given. So we can find b from the ratio of p over d. D is equal to 1.5 inch. So b over 1.5 is equal to 1 over 2. So b is 0.75 inch. Now we have to find factor of safety. For factor of safety we need p critical. So we can use any of the above, either horizontal p critical or vertical, because both are same. So p critical horizontal, let us use this one. Pi square into E into b d cube divided by 12 into length square. Length is given 7 feet, 7 into 12 inches, and then square. So p critical becomes 8.556 kilopounds. It is same either around vertical or horizontal axis. So factor of safety is equal to p critical divided by p, or p allowable. P is given in this problem. For part B it is 1.5 kilopounds. So by putting p equal to 1.5 kilopounds, 8.556 divided by 1.5. So factor of safety becomes 4.75. Factor of safety has no units. So we have solved the problem. What we have done is, we were told that p critical around vertical and around horizontal axis are same because factor of safety is same. So we have found expressions around p critical around horizontal and around vertical axis. We just need to know the equivalent length, effective length, which can be found from the given boundary conditions. I, we can find I. Always the depth direction has cube. So around horizontal axis d is the depth, around vertical axis b is the depth. By equating p critical vertical and horizontal, we have found ratio of p over d, and then putting all the values in the expression of p critical horizontal, we have found p critical. Either you can use p critical vertical or horizontal, both are same. And we have found factor of safety from this expression, p critical divided by p. Let us move further to the next numerical problem from the exercise. I have chosen problem number 1023. Problem number 1023 states is a 1 inch square aluminium strut is maintained in the position shown by a pin support at A and by sets of rollers at B and C. So it is given that this support is pin, here are rollers at B and C. Okay, this column can rotate in the given plane. We have already given, we have been given a two-dimensional problem here. So in the given plane, this column can rotate around this pin. So end A is pinned. End B or point B, the column cannot rotate in the given plane. It is fixed at point B. Similarly, it is fixed at point C and it cannot rotate in the given plane. Always remember it. We are solving it in the given plane. In some other plane, it can rotate around B or C, but in the given plane, it is fixed at point B and fixed at point C. But point D is free. There is no restriction at point D, no constraints. Okay. Another thing which is given 1 square inch. To find I, we must know that this column has dimension of 1 cross 1 inch. Okay, so I will be 1 over 12, 1 into 1 cube. Okay. Similarly, what other is known? Knowing that LAB is 3 feet, this is 3 feet, LBC is 4 feet, and LCD is 1 foot. Determine the allowable load P. P needs to be determined using a factor of safety with respect to buckling of 3.2. Factor of safety is given. Consider only buckling in the plane of figure. Remember it. We have to consider buckling in the given plane only. Either it is XY or XZ or whatever plane. We have to consider only this plane. Use E equal to 10.4 into 10 power 6 psi. So let us move further. Okay, a little more. Here we have 3 different types of boundary conditions. In portion AB, and A is pin support and B is fixed. So we have a column AB with one end pinned, other end fixed. For one end pinned and other end fixed, LE is equal to one end pinned and other end fixed. One fixed 0.7 L. Okay. Similarly, for second it is 0.7 L AB. For BC section, both ends are fixed. B is fixed, C is fixed. So when both ends are fixed, so it is equal to 0.5 L BC. And for CD section, one end is fixed, C is fixed, D is free, so it is 2L CD. So we have to divide this column in 3 sections. Let us move towards the solution. This is problem number 1023 from the exercise. Effective length of section AB is equal to 0.7 times LAB, which becomes 0.7 multiplied by 3. It is 2.1 feet. LE for BC section, it is equal to 0.5 times LBC. 0.5 into 4 becomes 2 feet. LE for length CD, it is one end fixed and other end free. It is 2 times LCD. 2 into 1 becomes 2 feet. So among these 3 lengths, length AB, it is the maximum one. The section with maximum effective length will buckle earlier than the other sections. So we have to consider LEAB because it is critical section. It has maximum length. In columns, the maximum length is always greater lengths are critical as compared to the smaller lengths. So maximum effective length has needs to be considered. This is our LE maximum 2.1 feet. I is equal to 1 over 12 1 into 1 cube because the cross section is 1 into 1, so it is equal to 0.08 333 inch power 4. P allowable needs to be found. It is equal to P critical divided by factor of safety. So factor of safety is 3.2. 1 over factor of safety into pi square E I over LE square. Vector of safety is given as 3.2. E is given, which is equal to 10.4 into 10 power 6 psi. I has been found 0.08333 inch power 4, and LE needs to be used as LE maximum, which is 2.1 feet. So by putting all the values, P allowable is equal to pi square into 10.4 into 10 power 6 multiplied by 0.08333 divided by 3.2. LE square, LE is 2.1 feet, so we need to convert it into inches, multiplied by 12. So P allowable will be 4.21 kilopounds. What we have done is, we have divided the column into 3 lengths. Actually it is given, 3 different lengths were given. So we have found equivalent lengths of each of the 3 sections, because boundary conditions are different for all the 3 sections. So the one with maximum length is critical. We have to consider that one. I is simple, 1 over 12 into 1 cube, because cross section is 1 into 1 inch, square inch. P allowable is equal to P critical divided by factor of safety. We know the expression for P critical. We have used LE maximum, or critical one. Factor of safety is given, so P allowable has been calculated. Let us move further towards the next problem. It is problem number 1024 from the exercise. Column ABC has a uniform rectangular cross section with B equal to 12 mm and D equal to 22 mm. B and D are dimensions of the column, width and depth. The column is braced in XZ plane at its midpoint C and carries a centric load P of magnitude 3.8 kilonewton. P is given, which is 3.8 kilonewton. In XZ plane, here is a rod passing through the column from point C, and the column has been constrained here using this rod. Knowing that a factor of safety of 3.2 is required, factor of safety is given 3.2. Determine the largest allowable length L. We have to find largest allowable length among the for this beam. The beam may buckle either in XZ plane or YZ plane. So we have to find allowable length for XZ plane and for YZ plane, and whichever among them is smaller, that is our largest allowable length. So first we need to know how this beam will buckle in XZ plane and how it will buckle in XY plane. So if we see in XZ plane, whenever this beam will buckle, it can slide on the on this rod which is passing through point C. So point C can slide to along the x-axis. So if we draw a two-dimensional model shape of this beam in XZ plane, how will it buckle? It will buckle like this. Sorry. If initially it is a column, it will buckle like this under load P. Remember that both the points A and B are pin-ended loads, pin-ended points. Okay, this is point C. So here is length L, here is length L, A, B, C. So portion AC or portion BC, both are similar to pin-ended columns. So here our effective length is equal to LE. This portion is similar to, in terms of model shape, it is similar to a pin-ended column like this one. So where LE is equal to 2L. Okay. For plane YZ. Okay, now if we see towards if we see from this direction towards the plane YZ, we can see that the column can rotate around this point C. So how we can plot the model shape in YZ plane? It will be, this is initial column, it will be like this. Column will buckle like this. So this total length between AB is 2L. So effective length is equal to 2L. This is similar to this model shape, is similar to both ends pinned column, pin-ended column we can call it, like this one again. But in this case, the total length, effective length is equal to 2L. In the previous case, the effective length was L. So we will use these two expressions for plane XZ and plane YZ to solve our problem. So let us move towards the solution of problem 1024. What we need to find is length, allowable length. We can find allowable length from the expression of P critical. First we need to find P critical. P critical is equal to factor of safety into P allowable. Factor of safety is given and P allowable are given. Factor of safety is 3.2 and P allowable is 3.8 kilonewton. So 3.2 into 3.8 becomes, in kilonewton, it becomes 12.16 kilonewton or 12,160 newtons. Okay. P critical is equal to pi square EI over LE square. From here we can find LE equal to pi into square root of EI divided by P critical. Okay, if we consider buckling in XZ plane, as discussed earlier, the model shape in XZ plane will be of this shape. So here the effected length is equal to L. Okay, so effected length is equal to L. LE is equal to L. So by putting it in expression 1, L is equal to pi to EI divided by P critical. Okay, E is given. I is equal to, I in this case will be, let us see it in horizontal, around the XZ plane. Okay, in terms of XZ plane, if it rotates in the XZ plane, this is our depth, B is our depth, so it will be dB cube divided by 12. I will be dB cube divided by 12. So it will be E into dB cube divided by 12 into P critical. Okay, we know all the values. E is given, B is given, D is given, P critical has been found, pi is a constant, so we can find length. By putting all the values, the length will be 0.7171 meters or 717.1 millimeters. Okay, this length has been found for buckling in the XZ plane. Let us find another length for buckling in YZ plane. We have already discussed that the buckling shape in YZ plane will be like this, where our affected length is equal to 2L, and in the YZ plane I will be BD cube divided by 12. So let us put LE equal to 2L in equation number 1. Here's our equation number 1. So 2L is equal to pi square root of EI over LE square. So L becomes pi by 2 square root of E. I is BD cube divided by 12, and sorry, this is P critical. Into P critical. Putting all the values, we know the value of B, D, E, and P critical has been found earlier here, this one. So by putting all the values, L becomes 0.657 meters or 657 millimeters. So among these two lengths, length 717.1 mm and 657 mm, this is the minimum length. So this is our allowable length. So largest allowable length is equal to 657 mm. You always need to consider the minimum length, because at the maximum length the column will buckle earlier, so we need to use the safe length, which is the minimum allowable length. It's the minimum length which is actually the maximum, the largest allowable length. What we have done is we have considered buckling in both XZ and YZ plane. In both these planes the model shapes are different because the column has been constrained at point C using a rod. By passing the rod through the column in the XZ plane, so the model shapes are different in XZ and YZ plane. In both the cases, LE is different. LE is equal to length in XZ plane and is equal to 2L in YZ plane. By using these expressions, we have put it in expression number 1. Expression 1 was found from Euler expression, and simply by putting all the values, we have found two lengths, one in XZ plane and another is in YZ plane. The one with the minimum value is the largest allowable length. Okay, let us move towards the next problem, which I have chosen from the exercise. It is problem number 1036. Problem 1036 is about an eccentrically loaded column. We can see here the load, applied load P, has an eccentricity of E. It is not passing through the center of the column. Okay, this column is a pipe shaped column. It has an outer diameter of 120 mm and thickness of 6 mm. Length of the column is 2.1 meter. Okay, the statement is a brass pipe having the cross section shown has an axial load P applied 5 mm from its geometric axis. So this 5 mm from geometric axis is actually 0.005 meter. Eccentricity E, this is value of E, okay. Capital E is given as 120 gigapascal. Determine in part A the load P for which the horizontal deflection at the midpoint C is 5 mm. Once this column buckles, it will buckle like this. So horizontal deflection at point C, it is Y maximum because point C is at the midpoint. It is 0.005 meters. 5 mm is 0.005 meters. So what we have to find is load P in part A, and for part B the corresponding maximum stress sigma maximum is unknown. So let us move towards the solution. We have to use secant formula in this case. Okay. Problem number 1036. E is given 0.005 meters. Inner and outer diameters are given. Inner diameter is 108 mm. Outer diameter is 120 mm. We can find I, moment of inertia, from these values, which is pi by 64 outer diameter power 4 minus inner diameter power 4. If we put the values, it is 3.5 into, first we have to convert it into meters. It is 0.108 meters, 0.120 meters. So the value will be 3.5 into 10 power minus 6 meter power 4. Okay. Since this column is pin-ended column, both the ends and A and B are pin-ended, so we have to use LE equal to length. For pin-ended column, effective length is equal to total length, which is given as 2.8 meters. Okay. First we have to find P critical, which is equal to pi square. Why we need to find P critical? This P critical is used in the expression of Y maximum. That is why I am finding it. Pi square EI over LE square. So by putting all the values, LE is known, pi is a constant, E is given, I has been found. So P critical becomes 528.73 into 10 power 6 newtons, or 10 power 3, this is 10.3, 528.73 kilonewtons. So for part A, Y maximum has been given and we need to find P. We know that Y maximum, expression of Y maximum from the theory part, it is equal to E into secant of pi by 2 square root of P by P critical. Here we need P critical, that is why I have found P critical earlier, minus 1. Okay, Y maximum is equal to 0.005. E is also equal to 0.005. Both are given. Okay. Secant of pi by 2 P by P critical minus 1. Okay. This becomes 2 equal to secant of pi by 2 into P divided by P critical 528.73. Okay, secant inverse 2 is equal to 60 degrees, and if we convert 60 degrees into radians, it is pi by 3 radians, and we can write secant inverse 2 is equal to pi by 2 square root of P over 528.73. Secant inverse 2 in terms of degrees, your calculators are usually in degrees, so you will find 60 degrees. Convert it into radians, it will be pi by 3. Always convert it into radians. We cannot simply multiply degrees with meters and newtons. In SI units we have to use radians. So pi by 3 radian is equal to pi by 2 square root of P divided by 528.33. So we can find P from here, which will be 235 kilonewtons, which was required in part A. It is P allowable. For part B, we were asked to find sigma maximum. So sigma maximum for eccentrically loaded columns is equal to P over A plus P over A plus M maximum C over I. P over A is stress due to normal loading, axial loading, and MC over I is due to bending moment. So we have already discussed this in our theory part. You can also use the direct expression of sigma maximum from the chapter. Okay, what is M maximum? It is equal to P into Y maximum plus E. We have already discussed this in the theory part. So putting all the values similarly, C is equal to half of the outer diameter. It is actually outer radius, which becomes 0.06 meters. Outer diameter is 0.12 meters, so outer radius is 0.06 meters. Similarly, area A is equal to pi by 4 into outer diameter square minus inner diameter square, which becomes 2.149 into 10 power minus 3 meters square. P is already known, 235 kilonewton. Putting all these values, I is also known. Initially, earlier in the problem, we have found I, which is 3.5 into 10 power minus 6 meter power 4. Putting all these values in this expression, sigma maximum becomes 235 into 10 power 3 divided by 2.149 into 10 power minus 3 plus 235 into 10 power 3. Y maximum plus E, 0.005 plus 0.005. C is 0.06 divided by I is 3.5 into 10 power minus 6. So sigma maximum becomes 149.65 into 10 power 6 pascals, or you can say 149.65 megapascals. This is sigma maximum, which was required in part B. So what we have done is, we were given a column, an eccentrically loaded column with an eccentricity distance of 0.05 meter. Similarly, Y maximum equal to again 0.005 meter. Luckily in this, coincidentally in this case, both E and Y are same, Y maximum. It will not always be same, so don't be confused with this. In some other problem, if you are given E, it doesn't mean that Y maximum will be similar to E. Okay, this is very important. We were asked to find P, allowable load, and sigma maximum stress. So Y maximum expression is already known to us from theory. We have in this expression only P is unknown. P critical was unknown, but we have found P critical earlier because we know the affected length is equal to total length. It was a pin-ended column. So we have found P allowable from the expression of Y maximum, and then we have used sigma maximum expression, which is equal to stress due to axial load plus stress due to bending load. So sigma moment maximum will always be equal to, remember this for the other problems as well, it will be equal to P into Y maximum plus E. We have studied it in the theory. C is always half of the outer diameter, it is outer radius, and area of the circle is pi by 4 outer diameter square minus inner diameter square. So we have put all the values in this expression and we have calculated sigma maximum. So let us move towards our next problem, which is the last one I have selected for this lecture. It is problem number 1039. This is again a pin-ended column with eccentric loading. So here we can see the load is not applied at the centroid of the column, but there is an eccentricity distance E, which is given in the statement. Okay, the statement is the line of action of the axial load P is parallel to the geometric axis of the column. Okay, so P is parallel to the y-axis, which is actually the geometric axis of the column, and it is applied at a point located on the x-axis at a distance of E equal to 12 mm. So this distance is given as 12 mm, which is eccentricity. Okay, the column is a W310 into 60 rolled steel column. So we can find the value of I from the appendix. Okay, length of the column is given, which is 7 meter. E is 200 gigapascal. In part A, we have to determine the load P for which the horizontal deflection of the midpoint C of the column is 15 mm. So P has to be found, P allowable or P. Horizontal deflection at the midpoint C. At the midpoint in the column, in the pin-ended column, midpoint always has maximum deflection. So this is Y maximum actually, 15 mm. In part B, we have to find maximum stress. Again, similar to the previous problem, we have to find sigma maximum. So this problem is almost similar to the previous problem, but in this case, we have to find I from the table. And you know that in this problem, E is not equal to Y maximum. So as discussed earlier, it is not always that E will be equal to Y. They are not similar. Now, since the load is a very important point in this problem is which is different from the previous problem. Why I have selected this problem? The previous problem was about an axisymmetric structure. So in this circle, wherever you apply the force, I will be same because it is axisymmetric. But here you can see force is applied along the x-axis. So this column will buckle in xy plane. In xy plane means this column will rotate around z-axis. This column will rotate around z like this. If I make a two-dimensional column here, so it is this is y-axis and this is x-axis. So force is applied here, P is applied here, this is y-axis, and the column will buckle in xy plane and it is actually rotating around z-axis. What is the z-axis of this column? If we see, this W column is like this. here. So we can see the Z is passing through the web of the section. So if we move to the appendix for W310 into 60 cross section, W10 360, W10 360. Where is it? W10 360. Sorry, W310 into. Let us confirm it again. W310 into 60. W310 into 60 is here. W310 into 60 is here. This one, W310 into 60. Here we can see the axis passing through the web of the cross section is y-axis. We have to find I for the axis passing through the web. So in our problem it is z-axis, but actually in the appendix it is y-axis. So we have to use IY, which is 18.4 into 10 power 6 mm power 4. Similarly, we can use this SY section modulus as well. We will need it. It is 180 into 10 power 3 mm cube. So let us use these two values. We will need SY. Why we will need SY? I will tell you. So let us note these two values, 18.4 and 180, and let us move towards the solution of the problem. 1039 IZ. In our problem it is IZ. In the appendix it is IY. So here we will write IZ because we are solving this problem. It is 18.4 into 10 power minus 6 meter power 4. It was 10 power plus 6 millimeter power 4, so we can convert it into meters. 10 power minus 6 millimeter power 4. Okay, area of the cross section is also given. We will need the area as well for P over A. Area is 7550 millimeter square. 7550 millimeter square. SC from the table is 180 into 10 power minus 6 meter cube. In the table it is given in millimeters. I have converted it into meters. Okay, first I want to find P critical because we will need it in the second formula. P critical is equal to pi square EI over LE square, because both ends are pin ended, so LE is equal to L, and we can put all the values here. Pi square, E is given as 200 into 10 power 9, it is 200 gigapascal. I is 18.4 into 10 power minus 6. It is very important to use appropriate I in this problem, otherwise the solution will be wrong. L is given as, let us check it again, I think it is 7 meters. Okay, so 7 square, so P critical becomes 741 into 10 power 741.23 into 10 power 3. So for 10.3 I will write 10 power 3 I will write kilo. It is 741.23 kilonewtons. For part A we need P, similar to the previous problem. Y maximum is equal to E into secant of pi by 2 P by P critical minus 1. E is known, Y maximum is known, P critical is known. By putting all the values in this expression, we can find P. So let us put all the values in this expression. It is 0.015 meters equal to 0.012, this is value of E, secant of pi by 2 P by P critical is 741.23 minus 1. Remember that you have to convert the angle into radians. You have to use radians in SI units. So solving this problem, I will directly write it here. You can do the simplifications by yourself. P becomes 370.29 into 10 power 3 newtons, or simply 370.29 kilonewtons. This was required in part A. In part B, sigma maximum was required, which is equal to P over A plus M maximum C over I. Or we know that I over C is equal to S, so we can use it here, P over A plus M maximum over S. That is why I have found S from the column, from the appendix. We can simplify this expression and directly use S here. Okay, S will be in the same direction as I. So we have found IZ and SZ. M maximum again, it is equal to P into Y maximum plus E. So sigma maximum is equal to P is known, 370.29 into 10 power 3. Okay, area is known in millimeters, so we can convert it into meters. It will be 0.007550 meter square, plus moment is P into Y maximum plus E. So P is again 370.29 into 10 power 3. Y maximum is it is given 0.015. E is 0.012 divided by S. S was found earlier. It is 180 into 10 power minus 3 meter cube, this one. So 180 into 10 power minus 6 meter cube. Okay, simplifying this term, sigma maximum can be calculated as 104.58 into 10 power 6 pascals. So I will write it as 104.58 megapascals directly. This problem was similar to the previous problem. The only difference was the eccentricity in this case, because it is not an axisymmetric cross section. So we have to see that in which plane the column is buckling, around which axis it is rotating. So we have to find I, the appropriate I, from the appendix. Since this was a W section, so appendix was given. If it is not a W section, if it is a simple rectangle, so you have to find I by yourself using the expression for moment of inertia, but you have to find appropriate I, around which axis the column is rotating. So we have found P from the expression of Y maximum. In some other problem, if P is given, you may be asked to find Y maximum. You will use the same expression. Similarly, you have to find sigma maximum from this expression. You need to use either MC over I or M over S. You can also use expression for sigma maximum directly from the book. It is given in the theory. Both of the expressions are okay. So this problem is solved. This was all I have. These problems, I have selected these problems for the students. I hope by covering these problems you can solve all of the other problems from the exercise. You can discuss your solution with me. For the other problems you can try, and if there is any difficulty you can discuss with me on my email address, which is given on my website as well. So I hope this was enough for this chapter. The basic concepts will be clear after this lecture. Thank you.